Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 3, and it is entitled Vectors and Scalars. In this lesson, we encounter the importance of handling effectively measured quantities in physics. Just what kinds of physical quantities are there? It turns out that there are several different kinds, namely scalars, vectors, and tensors. There are also quantities called pseudoscalars and pseudovectors. In this course, we'll limit our attention to scalars and vectors. Your authors give a decent explanation of scalars and vectors in your text, and you should read and try to digest what they say about them. Briefly, a scalar is a quantity that can be represented by a number only. We call that number the magnitude of the quantity. A couple of examples of scalar quantities include mass, so how many kilograms do I have? Temperature, how hot or cold is it in my room? The time of day, or how much time elapses between one event and another. Each of these quantities can be represented by a number only. On the other hand, a vector is a quantity that must be represented by a number, which is called its magnitude, and a direction. Some examples of vector quantities include force, so how hard do I push, but also which way, how many pounds, and in which direction, to the right, to the left, up, down, at what angle. Velocity is an example of a vector. Acceleration is another example, and we'll encounter many more in this course. The mathematics of combining scalars is straightforward. You handle them using the regular rules of arithmetic that you've learned in the math department. The mathematics of vectors, however, is a little more tricky. You'll learn how to deal with vectors in the math department as well, but we'll teach you about them in this lesson too. Graphically, we represent vectors using arrows. The length of the arrow on an appropriate scale represents the magnitude, and the angle the arrow makes in a given coordinate system represents the vector's direction. So that means we'll be using a ruler to construct the magnitude of the vector, and we'll use a protractor to construct the direction of the vector. Once the vector is constructed, we can think of the vector as the hypotenuse of a right triangle. We'll call the legs of that right triangle the components of the vector. There's a horizontal component, which we'll call the x component, and there's a vertical or y component, and frequently we'll use all three parts of the vector in the problems that we'll solve. You can use the mnemonic SOHCAHTOA help you figure out the parts of the vector in order to solve the problems you'll be faced with. Let's take a look at a couple of examples of constructing vectors and finding their components. Here's the first example, example 3a. Vector f equals 90 newtons at 30 degrees. Resolve vector f into its horizontal and vertical components. The first thing I want to do is to represent this vector graphically. So I want to use a ruler and a protractor to construct this vector, which is going to be the hypotenuse of a right triangle. And then I'm going to use trig functions to figure out what the horizontal and vertical components are. Graphically, I have to decide on a scale. And depending on how you're viewing this particular recording, the scale that I'll draw and the scale that will appear if you were to actually measure it on the screen with a ruler may not appear equal to each other, but they will be consistent. I'm choosing a scale in which 1 centimeter is equal to 10 newtons. That means on this scale, my vector f, which is 90 newtons, will be 9 centimeters long, and I'll use my ruler to construct that vector. My vector is directed at 30 degrees. I'll choose a standard XY coordinate system in mathematics to represent this vector space. In this coordinate system, I have what's called quadrant 1, quadrant 2, quadrant 3, and quadrant 4. I have what's known as the plus x-axis and the plus y-axis. I also have a negative x-axis and a negative y-axis. I start at the plus x-axis, let that be equal to 0 degrees in my protractor, and then I go in the counterclockwise direction so that the plus y-axis corresponds to 90 degrees, the negative x-axis corresponds to 180 degrees, and the negative y-axis corresponds to 270 degrees. If I come back around to the x-axis again, that would be 360 degrees, and I will have been around the circle one time. I need to choose a place to put the origin of my coordinate system. Since this is a vector that's in the first quadrant, then I'll put my coordinate system kind of at the bottom left-hand side of the space in which I'm working. Using the origin of that coordinate system, I'll place my protractor at the spot where I can measure and then indicate 30 degrees with a mark. And then I will measure my vector 9 centimeters and direct it between the origin of the coordinate system and that 30-degree mark, and I'll make my vector 9 centimeters long. There's my vector, 9 centimeters long, which represents 90 newtons, and from the plus x-axis, it's up 30 degrees. Now I want to find what the x and the y components of this vector are. So I'll construct myself a right triangle. Going from the tip of this vector, I'll sketch down to make a vertical leg, and then I'll sketch across to make a horizontal leg. I'll call the horizontal leg Fx, I'll call the vertical leg Fy. The angle between the horizontal leg and the vector itself is the 30-degree angle. Now I need to figure out what is the x component and the y component of this vector. Let me recognize that the hypotenuse represents the vector itself. The side that is adjacent to the 30-degree angle is the horizontal side, or the x component, and the side that is opposite the 30-degree angle is the opposite side. Now I want to apply SOHCAHTOA. I know that the hypotenuse is equal to 90. I'm trying to figure out what is A equal to, that's the horizontal component, and what is O equal to, that's the vertical component. Let's start with the horizontal component. You need to make sure that your calculator is in degree mode when you do these problems. And now I have a mathematical equation. I can solve that equation. I multiply both sides by 90. Now I put in the numbers, and I get 77.94. And I'll go over here down to my right triangle and write that result in. Now I need to figure out what the vertical component is. I see that I have the opposite side in the hypotenuse. I see that the sine relates those things together, so I'll write another equation. The sine of 30 degrees is equal to Fy divided by 90. Now I put in the numbers, and I get vertical component is equal to 45 newtons. And I'll write that in to my triangle as well. Those are my answers. The horizontal component is 77.94. The vertical component is 45. The hypotenuse is 90. And the angle of this vector is 30 degrees in this particular coordinate system. Let's look at another example. Example 3b, part A. Vector D is 40 newtons at 0 degrees. Resolve D into its horizontal and vertical components. I'll choose to use the same scale in this vector as I did in the previous one. 1 centimeter is equal to 10 newtons. So on my scale here, I choose a coordinate system that has an origin at a certain point, and I draw a vector that's 4 centimeters long. There's my vector D. It's at 0 degrees, which means that it's along the horizontal axis, the plus x-axis. dx is going to be equal to 40 newtons. I could say that that's d, the hypotenuse, 40 times the cosine of 0 degrees. But you know the cosine of 0 degrees is equal to 1. dy in this case is equal to 0 newtons. There's no part of this vector that's along the y-axis. So you could think of this as a right triangle that has a hypotenuse that lies along the horizontal leg, and it has no height at all. Part B, vector E is 40 newtons at 180 degrees. Resolve E into its horizontal and vertical components. We play the same game. I choose a scale. Again, I'll use 1 centimeter is equal to 10 newtons. I'll put a coordinate system. I'll sketch my vector. In this case, vector E points along the negative x-axis. So I would say that Ex, the x component, is equal to negative 40 newtons because it's in the negative x direction. Ey is equal to 0 newtons again. If you wanted to, you could say Ex is equal to E times the cosine of 180 degrees. And the cosine of 180 is equal to negative 1. So I again have a right triangle whose height is 0 and whose horizontal leg is equal to the hypotenuse. Now let's talk about combining vectors. Typical vector combinations include vector addition and vector multiplication. In this lesson, we'll do vector addition, and in a subsequent lesson, we'll take up vector multiplication. When we add vectors, we end up with a resultant, which is the result of the vector addition. That's why it's called the resultant. One approximate method is called the tail to tip graphical method, and it involves sketching vectors to scale, placing the tail of one vector at the tip of the prior vector, and then sketching the resultant from the tail of the first vector to the tip of the last vector. The length of the resultant is measured on the scale you choose, and the angle of the resultant is measured using a protractor. The more common way we'll combine vectors is what your authors call the mathematical method, and I call it the analytical method. This method produces an exact result using trigonometry and the Pythagorean theorem. Let's demonstrate both of these methods using a couple of examples from your textbook. The first example is 3.1. Mathematically, find the resultant and the equilibrant of these two vectors, 4 meters at an angle of 20 degrees and 10 meters at an angle of 210 degrees. We begin by sketching a graphical construction of this. Now I have to do some planning ahead, so I see I've got a couple of vectors. One is in the first quadrant and one is in the third quadrant. The first vector is shorter than the second vector is, so my resultant is probably going to be in the direction that's where the longer vector is. So I have to plan ahead and put my origin somewhere kind of in the middle of my paper. I'll use the same scale I did before or a similar scale. I'll choose the scale in which 1 centimeter is equal to 1 meter of the vector. I construct my first vector. Now I go to the tip of that vector and I construct a new origin that has the same orientation as the first origin does. From that origin, I'll construct the second vector to scale. Now I construct my resultant vector. My resultant vector begins at the tail of the first vector and ends at the tip of the last vector. The angle that my resultant makes, I measure with respect to where its tail is. So I want to measure using a protractor that angle, and I want to measure this length, and that, according to my scale, will be my graphical resultant. According to my ruler, I get a length of about 6.1 centimeters, so that would correspond to 6.1 meters. And using a protractor, I measure that angle to be around about 217 degrees. So my graphical resultant is 6.1 meters at 217 degrees. Now I want to find the resultant analytically. I'm going to call the first vector here vector A, and I'm going to call the second vector vector B. And I want to find what is the length of AX and AY, and then I want to form a right triangle out of my second vector and find what is the length of the horizontal part of that, which I'll call BX, and the vertical part of that, which I'll call BY. Finally, what I'm going to do is to construct a right triangle out of the resultant. I'll call the resultant R, and it has an X part and a Y part. Now from this construction, I can see that RX plus AX is equal to BX. So that means that RX is going to be equal to BX minus AX. And likewise, from this construction, I can see that AY plus RY is equal to BY, so that RY is going to be equal to BY minus AY, if I'm thinking about magnitudes. So now I need to figure out what is AX and what is AY, what is BX and what is BY, and then combine those things using this relationship that I see geometrically. So if I concentrate on the A triangle, and I'm not drawing this to scale, A has a hypotenuse of 4, and it makes an angle of 20 degrees with respect to the horizontal. So AX is going to be A times the cosine of 20 degrees, and AY is going to be A times the sine of 20 degrees, using my SOHCAHTOA relationships. I find that the horizontal component of the first vector is 3.76 roughly meters, and the vertical component is 1.37 meters. I'll write that in to my triangle up here. Now let's concentrate on the B triangle. Again, I've not sketched this to scale, but I've sketched something where I've got a 30-degree reference angle for the 210-degree angle that we originally had to start with. Now, Bx is going to be 10 times the cosine of 30 degrees, and By will be 10 times the sine of 30 degrees. And I'll write those values in